It's like change the program. One will give the next talk. It's about inferring time-varying signal over graph based on partial difference equations. Linked to the previous talk is like saying time-varying functions on the nodes, basically. It depends on the language you speak with here. And he's a senior PhD student with my field here.
Hello, everyone. I'm going to talk about one of my latest works on inferring time-varying signals over graphs, so SPDEs. I'll explain it a little bit. First off, let's talk about multivariate time series over networks and some examples of them that we have, like, for example, in financial networks, when the network is basically correlation related, we have the stock prices over time over each node. Or in brain recordings, we have a proximity-based network, and we have the recordings, each recordings on different parts of the brain. Or like in a complete physical network, like a water network, we have some nodes in the city, they are connected by pipes, and they have some measurements over each node, like the pressure or height of the water there. And this sort of data has both spatial and temporal dependency. Some things change through time, and also they are connected in a network. One of the generic way to model all these different type of networks is just graphs, basically. For example, again, in the water network, the structure is a graph, and the time series that we have can be represented as a time-varying data assigned to the nodes of this graph. And let's just get some notation out of the way. Like here, we have a node set V, H set E, and the data recorded at each time is represented by XD, which is of dimension of the nodes, over a graph that we usually represent it with a matrix, either adjacency or Laplacian or any normalized version of this. So now I'm going to talk about the space and state models for the state and space model for graph signals or generally time-varying graph signals. Assume those time series we have are these observations Y here, and the space and state models assume that there is a well behavior latent in the space, which is hopefully first order Markovian, which means like at time t, it only depends on t minus 1. And because we're dealing with networks, we also expect this Markovian process, it depends on our structure. Okay. So in more formal notation, we assume our observations at each time are a function of the state plus some noise. And our state evolved based on the structure of the graph and only the previous sample first order Markov.
Sorry.
Yes.
If you make the exact, like if you contextualize to the water networks, what everything, like the state, what would represent in this case?
Generally, it's sometimes it can come from a physical system, right? They know, like, for example, the speed depends on the state of the acceleration or something in basic physics. But here we're mostly interested later on in a parameter estimation and like learning the state.
Yeah, but like the YT will be your multivariate time series, right? The YT.
The YT, yes.
And the XT, what would in the water networks, for instance, what would that be?
It would be another multivariate time series, but like because later on we train it, we learn it, we don't have any like physical representation. It's a latent value.
And you use it for?
Like to interpolate or just model the data, right? Later on, you can interpolate it and you can predict, forecast.
Okay.
So yeah, basically HMS.
Okay. Yeah.
So a very popular way to model this state, first order Markovian are like first order PDEs. And here just I want to give you some intuition that it's like, oh, what we get if we use a PD as the state and why this state as this model can be interesting. So if we assume that there is a PD at our state, for example, we can consider heat diffusion that you just talked about over the graph, where we know the derivative of the data we have over the graph is a function of the Laplacian multiplied by the data itself. So if we go with a very naive Euler discretization, we get the xt transits from xt minus 1 with this inverse matrix, which can be approximated by some parameters polynomial over the Laplacian. Right. And in the context of graph signal processing, we refer to it as a graph filter. It's pretty interesting. And later on, if we bring the whole statistics model to this context, we can have some model like we go from the time series or our observation with some encoder to a state. In the state, we have a very structured evolution with some graph filters, and with the readout layer, we come back to the observation, which is very similar to if you add some nonlinearities in the middle, it's like similar to GNNs. So it was just a side note that GNNs can be seen inspired by an status space model with a PD over graphs in the state for motivation. So, but the main thing is that if I go back here, we have a PD in our state. There might may not find any FT such that such a well-behaved state exists. So it would be helpful if we allow some uncertainty in the state. So we say, okay, state doesn't strictly follow evolution, but it follows evolution up to some system laws. And it brings us to the stochastic differential equations. So our state is, again, heat diffusion plus some uncertainty, some Gaussian noise, which is spread dispersed over our system with by matrix S. And yeah, then just some technical things that this beta is usually referred to as Brownian motion, but I don't go deep in it, and S is like the dispersion matrix. So the problem here in our model is that this S has a lot of parameters. So later on, when we want to estimate parameters, it also needs a lot of data and cost instabilities. So we need to parameterize it with the structure of our graph that we have. The thing I did here is that I parameterized the matrix, the dispersion matrix S by an incidence matrix of the graph, which represent each node, each edge connects to each node, and some sort of uncertainty value over each edge, represented by alpha. And I got this final stochastic differential equation here, where the mean or the average is still the diffusion, but we have an uncertain part, which also encodes some structure of the graph, and we're gonna estimate it. And the main contribution that this stochastic part does, because you can see that the average or the mean doesn't change, but it allows us to have a Bayesian scheme for prediction, for the estimation of the parameters that we have. So this is the final model we have. Stochastic PD observation model, and we need also some initial state and white noise. And our inference problem basically is like we're given some observation y1 to yt, and we want to estimate graph filter parameters plus alphas. To do so, it's the first step we discretize it. Again, I don't go to the details here, but we can have a first order Taylor approximation for the PDE that we have. So we have the transition matrix based on our Laplacian matrix and the Gaussian noise with a certain covariance matrix, which is related to the structure of our graph and the parameters alpha that we have. So the first step, we need to recover the state that we have, the xt. For this, as the problem is completely Bayesian, there's a recursive closed form solution known as Kalman filtering, where it first predicts the steps based on the initial value that we had, and then based on the observation it receives in an online manner, it updates the predictions that it has of the state and keeps doing it through time. And when we have this Kalman filter, this Kalman solution, we have basically a likelihood function for our observations, which allows us to have a principled way to update our parameters of the model, HKs and alphas, basically. And the good thing here is that also we can update this likelihood recursively with the Kalman filter. So we have this likelihood here, where the main thing it does, the difference with having just minimizing norm 2 is that here it adds some sort of an uncertainty in the middle of the norm. So wherever it has a high confidence, it forces the model to give a high weight to the estimation. So it's when the model have high confidence, it should have a less error and so on. And also, this can be solved recursively again by any solver like gradient descent or in a batch situation with expectation maximization. So for some final results, we tried some interpolation tasks on different data sets where we have missing data. And based on what we have, we're trying to impute them. This GSPD is the model we proposed. It's like, and we compared it with some very basic models. LMS is just an online model for time series, and SRGP is a graph based, and that considers graph also into account, and we work slightly better than that. In other data sets, we also have this ablation study here where we don't consider alpha at all, which means basically there is no stochasticity, and we just go with norm 2 and minimization of the diffusion, the heat diffusion problem. And another case when we have fixed alpha, and we are also learning the whole metrics of the dispersion. And generally, and this when we learn the dispersion matrix, it works a bit better than these two other cases, but it cannot still outperform the main model due to it has a lot of data. And all of these experiments are trained when there is not much data. There's a lot of missing values. It's, I think, I don't mention it here, it's around 40% missing values, and but there are not a lot of data. This whole matrix has a lot of parameters. It's a little bit tough to estimate it. So it shows that parameterizing it to the graph is working, and also into the forecasting path. extrapolation, the prediction step in the problem filtering actually helps the model to and keep the performance in higher prediction horizons, unlike when we don't care about the estimating the noise and compensating for it, because the main thing is about this system also is that it ramps up, because we keep when we have this process at time t to t plus 1 we have some error, it ramps up with the next error and so on and so forth. And here we show that compensating for it, it's this will improve the performance through time for the higher prediction horizons. And here are my references, and thank you very much. And I really have any questions.